So welcome to the June 2020 version of the Liftoff webinar series brought to you by Lyft. Today we're happy to welcome Temper Inc. to talk about current and future applications of smart susceptors. So I thank you everyone for taking the time to join us today. Hopefully everyone is remaining healthy and safe as we're all getting used to our remote, in many cases, workplaces. And some folks may indeed be getting back to their places of work right about now. So I want to give you a little bit of information about Lyft before we get into Temper and what Bill is going to present. So Lyft is one of the 14 national manufacturing innovation institutes. We were established through the Department of Defense back in 2014. We have a 100,000 square foot facility down in the Corktown neighborhood of Detroit. If you are ever in the Detroit area, wish you would come on and visit us. We've got about $50 million worth of equipment, cutting edge manufacturing equipment, both on the metals side and on the composite side, as we share some space with Department of Energy supported Institute IACME. We also have a learning lab in which we're educating and providing credentialing opportunities to the next generation of advanced manufacturers. We take about 120 students there at any time, any given day. When school is in session, unfortunately, we had to close that down a little bit early this year. But at Lyft, we are all about solving the manufacturing equation. We are focusing on connecting materials, processes, and systems. And we do that through our technology program, which is the leading innovations for tomorrow, as well as the educational program that I mentioned, the learning innovations for tomorrow. And put those together, and that equals Lyft, where manufacturing, technology, and talent matter. We focus on a number of different things at Lyft. We focus on accelerating technology. We focus on developing talent. We also convene folks together, which is what you guys are participating in today. We certainly appreciate that. We are a trusted advisor. We have experts both in-house and across our ecosystem that can help guide manufacturers into better ways, smarter ways that they can be doing their particular jobs. We also are working on, I mentioned the $50 million high bay that we have at our Detroit facility. We are growing that into a technology showcase, really show manufacturers around the country what the art of the possible is when it comes to advanced manufacturing and smarter manufacturing and tying those materials, processes, and systems together digitally as well as in reality. And we are a connector. Again, we are supported by the Department of Defense, but we work with not only folks in the government, we work with industry, large companies from Fortune 500 companies to small startup companies, and we're happy to connect those and everyone in between. We also work with many universities around the country, putting their expertise and their knowledge to work to help us support many of the projects that we work on. So we look forward to you guys visiting us. You can follow us on the social media machines. At LinkedIn and Twitter, keep track of us there, but you can also reach out to us directly via phone and through our website at lift.technology. So thank you for indulging me for just a second. Right now, I want to hand off the reins to Bill Dykstra from Temper Inc. So allow me to make him the host of the presentation, and we'll make that switch hopefully seamless. If you do have questions, please use the chat function that is available through the Zoom toolbar. You can address those questions to me, and we can facilitate that Q&A at the end. And again, please put your phones on mute, and we will get the presentation up from Bill here momentarily.
Hello. Do you see slide 1 right now?
We do, and if you can put it in presentation mode, that'd be even better. Thanks, Bill.
Okay. it just,
Always love live webinars. There's could be a hiccup or two.
Can you hear me?
okay. Yes.
Oh, there we go.
Okay.
Perfect.
Okay. So good morning. My name is Bill Dykstra, and I would like to introduce the LIFT membership to Temper Inc. Now, since you can probably read these slides faster than I can read them to you, I will not attempt to do so. I'll just try to explain them to you and give you the background info. Temper was formed in 2001 as the lead research company under an auto body consortium NIST-sponsored research contract. This program was called hot metal gas forming. This consortium consisted of 17 member companies and was brought together to develop a process called hot metal gas forming as an alternative to tube hydroforming. Although successful, the applications were limited due to the changing appetite of the major OEMs that were in the process of actively switching from commercial grade steels to higher strength steels. In 2005, through contacts developed during the hot metal gas forming program, Temper was contacted by the Boeing company to conduct research using induction heating and to develop a new method to rapidly consolidate thermoplastics utilizing the power of induction heating and the ability of some materials to become non-magnetic at specific temperatures. Recently, Temper has been commissioned by the Boeing company to commercialize these technologies to the manufacturing supply base. Over the years, Temper has developed a niche in being able to conduct basic research and production. We have been successful at taking ideas from a TR level 2 and carry them forward to a full TR level 7, serving as designer, component developer, and system integrator. By building the entire system in-house and installing these systems for the Boeing company as a true turnkey system provider. But first, let's talk about the heart of the process. What is a smart susceptor? Let's first get some background info out of the way. All magnetic material has what is called a Curie temperature. That is the temperature at which, when heated, it becomes non-magnetic. Some materials, or more correctly stated alloys, have a more defined line than others. In addition, there are other things that affect the ability of the material to shut off at the desired temperature, such as alloy composition, material thickness, and induction heating frequency. But for now, let's just take a typical case of how and why it works. At the beginning of the heating cycle, the induced current is at the surface. As the smart susceptor material is heated, the temperature is increasing. The induction heating current path continues to become deeper until the induced currents cancel at Curie. This can be visualized with a simple demonstration here on chart 3. We all remember magnetizing a screwdriver or nail in the 5th grade. When a power source is hooked up, it aligns the atoms inside the item being magnetized, and the resistance to the current flow creates heat. Using an induction heating source with higher frequency, we are able to change the current path more of a surface path for electron flow in a continuous fashion. The advantage of using induction heating with smart susceptors allows for heat up of the parts at a very fast rate. Why? Because the restriction of the power density is removed. The smart susceptor material will only heat to the predetermined processing temperature and then stop heating. This allows for very high power densities over short periods of time, wherein smart susceptors can be heated from room temperature to processing temperature, which is measured in seconds. Utilizing traditional heating profiles such as resistance or liquid heating mediums, water or oil, rapid or even heating to a predetermined temperature is often very difficult to achieve. With resistance heating, each zone or element needs to be designed as an independent closed-loop system to be sliced and diced into forgivable working zones of maximum temperature and deviation. Even on a medium-sized part, these heating zones could number in the dozens. And these heat zones are very difficult to add or subtract once the tooling has been completed, relying on FEA studies to be conducted for heat loss in the design phase. In the world of plastics, Tempur has developed many different applications for the Boeing company. And up until recently, these developments have been kept largely confidential. Other than required publications for the end of program DOE report outs, Tempur has recently been commissioned to commercialize these patented processes. Why? To drive down costs within their facilities. Working with the Boeing company, Tempur has completed processes of many different configurations, such as plastics and titanium. Matched metal configurations work well for both resin-infused woven fiber, resin-infused tape, resin-infused tape that is cut into shape and pre-tacked together, or works especially well for resin-infused tape that is chopped. Ceramic tooling works well for creating low-volume parts of unlimited size. Truly, the only restriction utilizing Tempur's modular approach is the budget to work with. In addition, Tempur can create parts using a co-consolidation approach, in which if you look at the image in the lower left-hand side, we have a part that was made of 9 previously co-consolidated parts, and then they were co-consolidated in one final forming process. In addition, Tempur has also made thermoset tooling, utilizing the same process, but made into a flexible shape and vacuum bag arrangement. Tempur has designed, built, integrated all components, and installed the thermoset debulking blanket to debulk the Boeing 787 rear elevators, measuring 9 feet by 39 feet in size. It can be seen here the different configuration of tooling applications that have been made. The photo on the left shows a matched metal tool configuration set up for high volume production, and a heat map showing only the smart susceptor itself heating. The center photo shows the modular approach to heating the wing skin tooling under construction, and the photo on the right shows the even heating of a debulk blanket for a thermoset application. It would not be hard to envision the combination of heating blankets and ceramic tooling to create a reusable blanket for consolidation of boat hulls, wind energy blades, or other large application where a reusable vacuum bagging approach for each part could be made. We are now going to dive a little deeper into the rapid cycling matched metal tooling concept. First, you need to think of a traditional mold, wherein if you took approximately only the surfaces that touched apart and went into the upper mold and to the lower mold surface an eighth of an inch and threw the rest of the mold away, you would in essence have two eggshells. Now, if you selected these eggshells were made from a smart susceptor material that had a Curie temperature that equals the molding temperature you were looking for, now you place the eggshells inside the induction heating field, and then because the eggshells have very little mass, it takes very low energy requirement to heat. And conversely, it also takes very little effort to cool. Here you can see the die-forming smart susceptor shells in the center top image and the induction heating coils that surround the die-forming smart susceptor shells. In this side, we can see the construction method for both supporting the eggshells or the die-forming smart susceptor mold shells, but it's easy to say eggshells, and the method of supplying both induction heating power and cooling air to the backside of the die shell used in cooling the tooling surface. Remember, because there is very little mass associated with the die shells, it takes very little energy to both heat and airflow to cool them. We will detail the air cooling of the die shells a little more on the next slide. Diving a little deeper into the cooling system, you can see in the center picture both the blue line and the yellow path line. The blue line represents water circulation inside the induction heating coil. The water is required to cool the induction heating coils and to use the bottom cavity to do so. The top cavity is for air. Air is a simple method of cooling the backside of the smart susceptor mold surface. Temperatures exiting the compressed air holes can reach -100 degrees Fahrenheit, which allows for quick cooling of the smart susceptor die-forming shell. And finally, we see a performance chart showing the repeatability of the process. Now, this study was not designed to show speed, but was generated to show process repeatability. What we did was to heat the die-forming shell up to the processing temperature, and then, under the worst-case heating arrangement, slowly increase the temperature over 3 minutes. Then rapidly quench the tool to a recrystallization phase of the material and holding it for 3 minutes, and then finally quenching to less than 100 degrees F. In this case, we repeated the process 50 times. The graph at the lower center of the chart is showing 10 of 50 cycles. The maximum deviation at this point over 50 cycles was 7 degrees, and that was a range. We are now going to show a video, if I can get it to work. Can you see the ply cut stack?
Yes.
What slide? Okay. So there's no sound with this, so I'll just talk to it. So in this video, we show the ply cuts being cut and stacked, going into the die. And then the die is then closed to a preheat location. So here, this kind of shows the current path going around the smart susceptors. And now what you would see is the smart susceptors heating up. Obviously, red is the process temperature that we're looking for. Then as soon as it's at process temperature, we close the tool, and then that heat is conductively heats the blanks. So So there's a thermal mass in the smart susceptor, and that heats the blanks. And then you can see the 2 cycles for cooling. If I could just back this up for just a little bit. At the beginning, with thermoplastics, can't stop it. But with thermoplastics, especially with PEEK and with PEC, you have a recrystallization phase. So even though we can cool the tool a lot quicker, we can only cool it to a certain level. And then you have to hold that level while the material recrystallizes within a range. And then you can cool it the rest of the way as fast as you'd like. But while it's in this 450 to 550 degree temperature range, it has to be held for at least 45 seconds. Okay. And then you just cool it the rest of the way. And then you can just take the part out of the tool. Good? Any questions? Okay. I'll go forward. Slide 12. In this tool, we are tasked with making nylon 6-6 panels. Nylon with fiberglass. These panels were 90 thousandths thick and were produced in under 8 minutes. The majority of the time for this process cycle was spent allowing the heat to propagate through the material and holding the material at temperature through the glass recrystallization phase before turning on the air quench. Preheating the material and more experimental use of quenching would yield a process time, we believe, in the 4-minute time frame. This tool, we were able to make 60% glass PPPE material. The glass mat material was made using PPE resin infused glass filament and then chopped using a continuous chopping and placement process. We were able to make preforms for each part. Again, in this case, the majority of the process time was in preheating the part to the proper forming temperature. It was kind of like trying to heat insulation material. Preheating of the blank prior to forming will save time and improve equipment utilization. So just recapping the major advantages of both the laminated tooling and the cast ceramic tooling, we can look at chart number 15. Again, the laminated tool is good for making higher volume production tooling, but for making low volume and larger tooling components, nothing beats the modular ceramic tooling approach. In this case, in the case of the tool on the right, both halves were made in 3 sections each. As you can see here in the IMI tool that was completed for the Boeing company under a recently completed DOE project, DOE IMI DE EE 5780. These tools were constructed from fused silicon material and have been proven to take a beating. In addition, there is no size limit to these tools. You just keep adding modular sections. Here, you can see how the modular cast tooling was fabricated and assembled. Each section of the tooling was fabricated individually, and then using fiberglass rods were tensioned together, holding the ceramic in compression. Here is a look at the heart of the ceramic tooling, with the ceramic of the tool being hidden. On this chart, you can see the induction heating coils, the smart susceptor in a loop condition, a part call, and the composite part to be formed. On this chart, you can see more of the mechanics of the ceramic tooling. The loop smart susceptor is created by pinching off the smart susceptor at the ends using what we call susceptor presses. These presses are pinched together using an air bladder. In addition, you can see the tension rods that are in place in the tooling that keep the ceramic material in constant compression. On this chart shows the first large panel produced. It was produced from a PEC FC carbon fiber material from hand-cut tape that was hand-tacked together. This multi-thickness ply drop part had final part thicknesses between 1/4 and 1/2 inch thick, and the physical dimensions of the part are 5 feet by 15 feet in length. In addition, this tool was successfully run for an advanced material composition between 780 and 790 degrees F. That material is not commercially available. And finally, on slide 19, you'll see a cast ceramic tool that was adapted from a different tooling configuration to this configuration to make a complex contour plastic, thermoplastic part. In this experiment, all of the plies were pre-consolidated into 9 individual shapes. The main panel was pre-consolidated, and the tooling as shown using the air bladder as its final forming medium. It can be seen that the main panel had multi-thickness ply drops. Secondly, the same die was used, but with a different perimeter edge bar tooling, as you can see here on the outside. All of the components, as shown in the photo, are on the left, are straight, except the curved multi-thickness panel that was pre-consolidated in a previous operation. In the figure on the right, you can see how these straight pieces were matched up into the curved aluminum forming pieces. And you can see in the photo in the center as the part comes out of the mold, and on the part on the lower right, how beautifully the finished part is, truly showing how forgiving the process is. The chart in the lower center shows temperature process range between 730 and 740 degrees F. Now switching to heating blankets, or for thermal set parts. These are a completely different application of the smart susceptor technology. In this configuration, the induction heating current is set to a frequency of 350 to 400 kilohertz. And in this current is passed through Litz wire that is wrapped with smart susceptor wire. For those of you who are unfamiliar with Litz wire, they are very small copper wires, approximately 4/1000 of an inch in diameter, that are individually insulated and bundled together, providing for a very large surface area for the current to travel on in a very small space. What is so great about these wires is each turn of the wire will only heat to its predetermined temperature range and no more. That is, each turn of each wire acts independently, and combined with other points acts like 1,000,000 points of self-regulating smart susceptor points in a heating blanket configuration. You can see here that the photo above the Litz wire and the individual smart susceptor wires are wrapped around it. The individual wires are placed on uncured silicone sheets, rows, and then cured. In the upper left-hand corner, you can see a multi-thickness thermoset panel, and in the photo on the upper right, the same panel with a heating blanket placed over it. for conducting a series of heating testing. In the photo in the lower left, you can see the heating profile. Notice the light blue line is the thinnest area of the part. That is, this area made it to curie and stopped heating. And the thicker areas and the areas closer to the edge of the stainless steel plate that it is resting on are the colder areas. But these are all within the tolerance zone of the process. And in the two photos in the lower right side show the heating blanket and blur image of an earlier heating blanket. In the case of a debulking blanket, it was of the one that we made. It was made from 16 individual heating zones. Each individual heating zone was powered by an individual power supply. And as you can see, these configurations also can be made as large as you would like them to be. On slide 24, you can see two photos of the debulking system constructed by Tempur for the Boeing company that is currently in production. Make debulking parts for the 787 rear elevators at their West Jordan facility near Salt Lake City. It has currently produced over 400 wing skins and is responsible for quality increases. This process replaces the need for these rear elevator wing skins from being debulked using an autoclave at a utility cost reduction of over 2 orders of magnitude. In addition, it has freed up the autoclave from being its bottleneck in production of these wing skins and increased the available time in its autoclave by 200%. Also, in addition, in comparison to using an autoclave before, the processing time was over 10 hours. Now it's an hour and a half. And it's automatic. Just set the bag, punch the button, and come back when it's complete. For the autoclave, because it's a pressure vessel, someone needs to man it at all times. With this process, we were able to hold plus or minus 5.5 degrees for 45 minutes. And this chart is showing the collective of 192 TCs, all running at the same time and all within plus or minus 5.5 degrees. By the way, the tolerance, the spec for the process was plus or minus 10 degrees. Applications, aerospace applications, debulking of thick structures, consolidation of large structures, using prepreg materials, boats, wind energy blades. It's all possible using smart susceptors. Questions?
Awesome. Thank you very much, Bill. Certainly appreciate the presentation today. As you can see, if you want to reach out to Bill directly, he has his email address on the screen, as well as the phone number. And as a reminder, if you do have a question, please use the Zoom chat function and address the question to Joe Steele, and we can get them asked. We have a few minutes to ask some questions. So some of them did come in. Bill, does the temperature need to be the same over the whole tool, or can the curie temperature vary at different locations?
Okay, so yes, you could vary the temperature at different locations. If that was for what, we've never built one that way. Is that question regarding the match metal tooling, the composite tooling, or would that be for the debulking blanket?
That's a good question. Chris, who asked the question, I think you might be able to chime in here. We have some time to more specifically ask your question. Oh, he's talking about composite tooling.
composite tooling. We have never built one for composite tooling where you would end up with different heat zones in different areas. But it would be possible to build.
Are there benefits to that, or are there deterrents to that? Or is it just something you have not specifically done yet?
Something we've never done yet. We've never had a request.
Got it. Got it. Does it refer to different? Is it because of different materials, or are there big differences in thicknesses? Is that what would drive different temperatures in different spots?
I've got to believe that his question would be different materials in different areas for co-consolidating materials together. Because you would not have different temperatures for different material thicknesses, not using a smart susceptor, because what will happen is where there's a thick area, we're making some panels right now that are 2 inches thick, right? And they're 1 inch thick in one area and 2 inches thick in another. And the smart susceptor just heats the inch thick to whatever that temperature is. And then the 2 inch thick, it just continues to heat or put BTUs of energy into the material until it all comes up to the proper temperature.
All right, continuing on composite tooling, does the flux penetrate the composite part in the tool and generate induction heating in part in addition to heating from the smart susceptor?
Come again?
Does the flux penetrate the composite part in the tool and generate induction heating as well as heating from the smart susceptor?
This gentleman is referring to the coupling in of the induction heating into the carbon fiber, to the carbon fibers themselves.
Yeah.
What you find is that you end up with it becomes a shield. So the smart susceptor itself shields the carbon fiber. So no, it doesn't heat. That flux is always trying to couple into whatever is available to it. And so you give it the smart susceptor for it to couple into.
All right. I have a question on the induction wires you were talking about earlier. Is there any degradation to the temperature at which the induction wires stop induction?
No. So, for instance, what it is, in the present configuration where you're taking the smart susceptor wires and you're embedding them into the silicone, right? The upper processing temperature of that silicone blanket is going to be about 370 degrees, 380 degrees F. You really can't get silicone to go higher than that. And it's also the insulation on the Litz wire also, you really can't get higher than about 375, 380 degrees F, or the wires start breaking down, the silicone starts breaking down. So now, if you were able to get a higher temperature wrapping on the Litz wire, and you could definitely make higher temperature Litz wire applications, but you wouldn't be able to embed those in silicone. For instance, you could embed those in epoxy, and then the epoxy could be the tooling. For instance, heated tools don't necessarily need to be made with smart susceptor plates, right? Or a smart susceptor matched metal tooling, like in our example. What you can have is you can almost like a heated tool approach for making like wind energy blades or boat hulls or things like that. You could embed the wires directly into the tooling, and then the tooling then heats the part.
All right. Again, I would encourage you to if you have a question, please send it on over the chat function, and we'll get that question asked. In the meantime, I would encourage you to take down Bill's email address and his phone number here to reach out to him directly if you have any more specific questions or want to learn more about some of the processes and projects that he talked about that he talked about today. I don't know that we have any more questions, Bill, so I certainly appreciate the presentation, appreciate everyone's participation today. Again, this webinar is being recorded, and we will post it on our website shortly, so you can refer back to it or share it with folks who are unable to make it this afternoon. I want to thank Bill and Temper Inc. For their membership in LIFT and their presentation today. If you are interested in learning more about LIFT, you can contact us directly at lift.technology or our phone number at 313-309-9003. Looks like we did get a couple more questions actually before we sign off, Bill. What kind of consolidation pressures can the composite system take?
We have consolidated up to about 550 psi. Many, it depends. Your PPE material, you're going to find really good results at 50 psi. Your PEC material is going to be at about 125. Your peak is going to be at 150. But we've run experiments all the way up to 350 psi.
All right, they snuck that one just under the wire. So appreciate taking a couple of extra minutes to answer that question. Want to thank Bill, want to thank Temper Inc., and thank everyone for their participation today. Stay tuned to your emails for a replay of this webinar with our monthly newsletter that comes out from LIFT, and then also pay attention to your emails for future webinars. So with that, hopefully everyone has a great rest of the day, and stay safe out there. We will talk to you soon. Thank you very much.
Thank you.